Hey everyone, and welcome to this explainer. Today, we're diving into something absolutely massive. I want you to picture a machine. We're talking about a sprawling, interconnected geographical engine of just staggering proportions. It literally dictates the lives, the agriculture, and the daily rhythms of over 1 billion people. Today, we're decoding India's climate. We're going to break down exactly how this natural machinery operates, from the fundamental gears turning up in the atmosphere, all the way to those massive global disruptions that can throw a giant wrench into the whole shebang. So here's our roadmap for today. First, we'll cover the foundations: weather, climate, and monsoons. Second, the 6 key factors shaping India's climate. Third, the ITCZ, the actual monsoon engine. Fourth, we'll look at breaks, storms, and winter rain. And finally, number 5, El Niño's global disruption. All right, let's jump right into section 1, weather, climate, and monsoons. To really grasp this system, we need to draw a hard line between two concepts that honestly people mix up all the time. Weather is just the momentary state of the atmosphere. It's fleeting, right? It changes super quickly within a single day or a week. Climate, on the other hand, is the grand average. It changes so slowly it's almost imperceptible. To officially note a shift in climate, you're looking at average weather conditions over a really long time. We're talking 50 years or even more. So we aren't just looking at today's rain forecast, we're looking at a half-century of atmospheric blueprints. And that brings us to the absolute defining feature of India's climate, the monsoon. Now, a lot of folks use the word monsoon to just mean a heavy downpour, but scientifically, it actually refers to the climate associated with a complete seasonal reversal in the direction of the winds. India has what's called a hot monsoonal climate, which is pretty prevalent across South and Southeast Asia. For most of the country, this dramatic wind reversal brings rain from June through September. But, the system does have its quirks. For example, the coastal areas of Tamil Nadu actually get their rain at the beginning of the winter season. Moving on to section 2, 6 factors shaping India's climate. Now that we know what the monsoon actually is, let's look at the structural casing of our climate engine. Because India's climate doesn't just happen in a vacuum, it's strictly dictated by 6 distinct geographical factors. We've got latitude, the towering presence of the Himalayan mountains, the distribution of land and water, distance from the sea, altitude, and finally, relief. Think of this list as the physical hardware of our engine. Every single drop of rain and gust of wind is steered, blocked, or accelerated by these exact 6 factors. Let's hit section 3, the ITCZ, the monsoon engine. So the real question is, what's the spark that makes this massive machine run? What gets the wind moving in the first place? Well, the answer is the ITCZ, or the Intertropical Convergence Zone. This is the beating heart of the machine. It's a low-pressure zone located right at the equator. This is where trade winds converge, and because they're crashing into each other, it forces the air to ascend. It's essentially a giant vacuum pulling air upward and dragging winds toward it from all over. Let's trace exactly how this creates the monsoon, step by step. In July, this massive low-pressure vacuum, the ITCZ, shifts north to about 20 to 25 degrees north latitude, positioning itself right over the Gangetic Plain. This spot is sometimes called the monsoon trough, and it encourages a thermal low over North and Northwest India. Because the ITCZ has shifted, the trade winds from the southern hemisphere cross the equator between 40 and 60 degrees east longitudes. Then something kind of wild happens. The Coriolis force grabs those winds and literally bends them, making them blow from southwest to northeast. And boom, just like that, you have the southwest monsoon. When winter rolls around, the ITCZ simply moves southward, and the whole process runs in reverse. The winds flip from northeast to south and southwest, giving us the northeast monsoon. Which brings us to section 4, breaks, storms, and winter rain. Now, this next part brilliantly shows that our engine isn't perfectly smooth. It has hiccups, dry breaks, and some pretty extreme byproducts that drastically alter daily life. You'd probably think the monsoon is just months of continuous rain, but there are actual breaks in the monsoon. And what's really fascinating here is that these breaks happen for completely different, highly localized reasons depending on where you're standing. In northern India, the rains usually fail if the rain-bearing storms just aren't frequent enough right along that ITCZ monsoon trough. But then look at the west coast. Dry spells there happen when the winds decide to blow perfectly parallel to the coastline instead of pushing inland. The engine stutters, sure, but for totally different reasons. And ma'am, this engine produces some intense heat too. Right in the heart of the ITCZ in the northwest, you find the Lu. These are brutally hot and dry winds that blow in the afternoon, and very often they just keep going right into midnight. It's this heavy, oppressive heat that completely blankets the region. But nature usually provides a localized relief valve. During May, in states like Punjab, Haryana, eastern Rajasthan, and Uttar Pradesh, you get these temporary evening dust storms. Now, I know a dust storm sounds pretty awful, but over there, they actually bring a highly welcome respite from the oppressive heat of the Lu. They bring along light rains and this wonderfully pleasant, cool breeze. However, when you start mixing the different air masses generated by this system, things can get pretty dangerous. Occasionally, moisture-laden winds get pulled toward the edges of the monsoon trough. And when you get a sudden, violent collision between those moist air masses and the dry ones, watch out. You get local storms of massive intensity. We're talking torrential downpours, violently destructive winds, and even severe hailstorms. But what happens when the engine shifts into its winter phase? Well, the winter precipitation effects are incredibly vital. Over northwestern India, weak temperate cyclones drifting all the way from the Mediterranean Sea bring meager but absolutely crucial rainfall to places like Punjab and Delhi. Why does this matter? Because it's a lifesaver for the rabi or winter-sown crops. On top of that, this precipitation falls as snow in the lower Himalayas. And it's exactly this snowmelt that sustains the water flow in the Himalayan rivers all through the blazing summer months. Meanwhile, as the northeast monsoon crosses the Bay of Bengal in October and November, it picks up a ton of moisture and unloads torrential rainfall over the coasts of Tamil Nadu, southern Andhra Pradesh, southeast Karnataka, and southeast Kerala. And finally, Section 5, El Niño's global disruption. Let's move to our last segment and see how this perfectly balanced engine is vulnerable to disruptions from literally halfway across the planet. It's a critical question. We've spent this explainer looking at latitudes, local troughs, and regional winds. But what happens to the localized Indian weather engine when global oceanic currents suddenly shift? Enter El Niño. El Niño is a highly complex weather system that rears its head once every 3 to 7 years. It messes with both oceanic and atmospheric phenomena. It gets its name, which translates to Child Christ, because it typically shows up around Christmas time in December. What essentially happens is an extension of the warm equatorial current temporarily replaces the normally cold Peruvian current, also known as the Humboldt current, way over in the eastern Pacific. Now, really consider the sheer scale of that replacement. The warm current spikes the temperature of the water on the Peruvian coast by a staggering 10 degrees Celsius. Just imagine the astronomical amount of thermal energy it takes to heat an entire ocean current by 10 degrees. It's mind-boggling. That massive temperature spike kicks off a chaotic global domino effect. First, it distorts the equatorial atmospheric circulation. Second, it causes massive irregularities in how seawater evaporates. This warmer water even causes a steep drop in plankton, which then completely ravages local fish populations off the coast of Peru. But zooming back to our main focus, India actually uses El Niño to forecast long-range monsoon rainfall. Because when El Niño happens, the Indian monsoon gets totally hijacked. For example, during the wild El Niño event of 1990 to 1991, the onset of the vital southwest monsoon was delayed over most parts of India by anywhere from 5 to 12 agonizing days. Which leaves us with this final thought. We've seen how meticulously structured India's climate is, driven by the steady rhythm of the ITCZ and geographic borders. But if a warming current thousands of miles away off the coast of South America can single-handedly delay the very monsoon that feeds millions across the Indian subcontinent, well, it makes you wonder, just how fragile is our interconnected global climate engine? Thank you so much for joining me for this explainer. I really hope this helps you see the invisible forces shaping our weather a little more clearly. Until next time, keep questioning the world around you.